Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
You know, every single second, humanity generates roughly 1.7 megabytes of data per person on Earth. Just think about that for a second. It's an absolutely incomprehensible amount of information. Today, on The Explainer, we're going to break down exactly how modern computers manage to process that massive scale of data at literal lightning speed, all without just, well, instantly crashing under the weight of it all. Let's dive right in. We are basically living in a massive data deluge right now. Historically, computing architectures relied on what's called serial execution, which means processing instructions strictly sequentially, one right after the other. But when you're dealing with the sheer scale and velocity of modern information streams, sequential processing becomes a hard, undeniable bottleneck. I mean, think about it. A system that has to completely finish task A before it even glances at task B simply cannot keep up with complex, real-time demands. We fundamentally needed a totally different paradigm to handle modern processing. Section 1. What is parallel computing? So, parallel computing is the architecture that swoops in and fundamentally saves our systems from that sequential bottleneck. By having multiple processors or even entirely separate networked systems attack different parts of a problem simultaneously, the whole paradigm shifts. We go from waiting in a frustrating single-file line to suddenly opening up multiple concurrent lanes of traffic. It's a highly optimized approach to resource management, giving us the amazing capability to solve incredibly complex algorithms in just a fraction of the time it used to take. Section 2. Dividing the work. The real secret here relies heavily on a classic divide and conquer strategy. We take a massive, computationally heavy task and intentionally shatter it into smaller, far more manageable subtasks. Then, instead of forcing one main processor to bear that entire load and risking a nasty thermal bottleneck, an entire array of processing units attacks those subtasks concurrently. It's a super elegant deployment of raw hardware to solve what is essentially a massive mathematical roadblock. Now, it's absolutely vital we distinguish parallelism from concurrency here, because they get mixed up all the time. Parallelism is the physical act of dividing a task up and running those pieces simultaneously on multiple processors. It's strictly about simultaneous execution. Concurrency, on the other hand, is a broader structural concept. It's the system's underlying ability to manage and juggle multiple tasks at once, regardless of whether they're executing at the exact same microsecond. Think of it like this. Parallelism is the raw power doing the heavy lifting, while concurrency is the master orchestrator keeping the whole system from falling into gridlock. Section 3. Threads and networks. We typically execute this parallel work in two highly distinct environments. First up, multithreading. This happens within a single process, utilizing smaller execution threads that actually share the exact same memory space. This approach is insanely efficient for maximizing a single machine's internal resources without introducing severe latency. But then we have distributed computing, which takes a fundamentally different route. It spreads the heavy workload out across completely separate computers connected over a network. This totally bypasses the physical limits of a single motherboard, allowing us to scale our sheer compute power almost infinitely. Section 4. Measuring the speedup. To prove this entire architecture is actually worth the underlying effort, we calculate what's called the speedup. This is the precise measure of performance gain we achieve by parallelizing a task versus just running it sequentially the old-fashioned way. It's the essential metric that justifies the computational overhead of breaking tasks apart and orchestrating them in the first place. Because, orchestrating multiple threads does carry an inherent cost. So the speedup proves mathematically that concurrent processing is undeniably the absolute champion of modern architecture. Parallel computing has fundamentally shattered the bottlenecks of legacy systems, expanding our processing limits exponentially. So the real question for us is, with this kind of raw architectural power right at our fingertips, what massive complex global challenges are we finally equipped to solve next? Thanks for joining me on this explainer, and keep questioning what's next.